A cannon fires a projectile at 45-degree angle from the horizontal at an initial speed of about 70 meters per second. Assume the ground is level and air resistance is negligible. You can use g equals 10 meters per second squared for the question to simplify calculations. How far away from the cannon in the horizontal direction will the projectile land? Alright, so when the projectile is launched, it's going to have a certain initial velocity and a certain initial speed. We'll want to find VIY and VIX to get started. So VIX will be 70.711 cos 45, which is just 50 meters per second. And then VIY will be 70.711 sine 45, which is the same, 50. Alright, we'll want to figure out, when that thing comes back down, how long does it take? Alright, so you have the option of using delta y equals 1/2 at squared plus VIYT. You could set the delta y as 0 because it'll come back to the same elevation that it was launched from. We used that in the past. (5t squared plus 50t equals 0, so therefore 0 equals t, 5t plus 50. T is 10 seconds. Alright, now I want to find out what is the speed of the projectile as a function of time. Okay. So I want to put the cannonball into a position vector like I did last time. Now how can I do that? Well, the thing's going to make a parabola where its speed is going to change. Like its speed will actually decrease as it goes toward the peak, and then it'll increase as it comes back down. But one idea is that it has a lot of vertical velocity at the beginning, and Earth pulls down in order to kind of counteract that and like take some of that away. So it slows it down. So what I would do is try to come up with an expression for the position of this cannonball as a function of time. Now, in order to do that, though, you have to come up with what is its horizontal and vertical velocity, though. So we already know the horizontal velocity is going to be constant. So we could set this to like a 50t for the I component. Then we can start off at a t equals 0 and just kind of steadily move toward the final location where it hits, and that can actually be t equals 10 when it hits. But now, how do you come up with an expression for the vertical position? Well, you may wish to do what I did in my previous problem, which is to consider what would the acceleration of this object be. It would be 0 in the horizontal and negative 9.8 or negative 10 in the vertical. Then you can come up with your velocity function by integrating. It's going to be 50 for the horizontal. All right, so when you integrate the negative 10, you have to, of course, have your constant at the end. So it wouldn't just be negative 10t. It would be negative 10t plus some initial VIY. So it would be plus 50 because that is what we had found here. Then you'd have that. Then you'd integrate one more time to get the position, and it would be negative 5t squared plus 50t plus some initial yi. But yi is ground level. It's 0. So we don't need that. So we'd have that. Let's see if Desmos agrees with that. So we'll do 50t comma negative 5t squared plus 50t is what we found. There we go. Perfect. But that'll do it. That's our cannonball. Apparently it goes 500 feet. And what we ultimately want to do in this section is find out how long of a path is that. We want to find the arc length of it, it's called. Alright, so first let's find the speed, like it says. Notice that I have an expression for the velocity, but I don't have the speed yet. To get the speed, what you have to do is you take the square root Alright, so plug in your formulas that you got above. 50 plus negative 10t plus 50 Now you could try to simplify that. So 2500 plus, well, it'll be 100t squared minus 1000 t plus 2500. Alright, so that's 100t squared minus 1000t plus 5000. I would like to, if possible, get the constant out of there. So I'd like to basically factor out the 100. And then we would get 10 square roots of t squared minus 10t plus 50. Now, what do we have to do in order to find the arc length, and why is the speed important for that? The reason why it's important is you've got your projectile path. Take any one instant along the path. There's going to be a speed or like a velocity vector. Let's say that's v, and then v is dr over dt. And so if you rearrange this, you get that dr equals v times dt. What it says is a tiny displacement equals the velocity times a tiny time. All right, we could also write it in its scalar form, which would be ds equals the speed times the tiny time. All right, and that's the formula we want to use to integrate to find the arc length, because the ds is like a length. All right, now what you want to do is integrate both sides of this. In other words, the arc length, the total arc length, can be found by integrating the speed of the projectile with respect to the time variable t, and we'll go from some initial time to some final time. Alright, so how do we set that up? We just have to make an integration where we put our formula for speed as the thing being integrated. Alright, so we'll do 10 square roots of t squared minus 10t plus 50 dt. We want to go from an initial time of 0 to a final time of 10 seconds. And that will give us our arc length. It's something that you can plug into TI-84 calculator, and it'll give you an approximation of it. There is also an antiderivative that you could plug into to also get that answer. So you could also try Symbolab for it. So hold on, let me bring up Symbolab and see if it can evaluate this. Alright, so here's Symbolab. We'll go from 0 to 10. 10 square roots of t squared minus 10t plus 50 dt. 574 meters for our arc length. And we just want to check it, like make sure it makes sense. Yeah, so the range of our projectile is 500. So I think it is conceivable that the path here could be just a little bit over 574 meters.